So welcome to this talk entitled as Faultless to a Fault, the case of threshold implementations of crypto systems versus fault template attacks. So this talk will be presented by myself, uh, Devdeep Mukhopadhyay. I'm working as a professor in the Department of Computer Science and Engineering at IIT Kharagpur. We are associated with the lab, which we call a Secured Embedded Architecture Lab or SEAL Lab, which with the focus on embedded security and side channel attacks. So with this brief introduction, I would like to mention the agenda of today's talk. So I will be starting with preliminaries on fault template attacks and then discuss about a double error upset, which is a fault model that we use in the attack FTA star. I will be introducing on positive Davio's decomposition technique that we use in this attack. I will be trying to talk about threshold implementations versus FTA star and talk about a graphical interpretation of FTA star and conclude my talk with some experimental results. So we all know that faults are extremely important in the context of cryptography because of several hardware accelerators or cryptographic accelerators being developed for ASICs and FPGAs, which raises concerns regarding their reliability. And faults are catastrophic in the context of security because our prior work shows that even mathematically secure algorithms like AES can be broken with a single well-formed faults. So therefore, there are different fault attacks that have been developed with different assumptions and different methods like DFA, DFIA, PFA, CIFA, and so on, which are all examples of non-profile attacks. The first example of a profile fault attack or a template fault attack was proposed in Eurocrypt in 2020, where we showed about how the fault propagation through gates, like for example, in this slide, we show fault propagation through an AND gate, which depends on the value of the unfaulted inputs, can be utilized to develop attacks which are called as fault template attacks. So using a systematic method, we try to get the values of all the unfaulted inputs just by knowing whether if the output is correct or faulty. So using these techniques, it kind of threatens or like has got the potential to bypass combined countermeasures, can attack middle rounds because it works without plain text or ciphertext access. So what are the exploits of these fault attacks? Many of the fault attacks that have been proposed before, they are non-profile attacks and require access to ciphertext, meaning that they are restricted to only the starting and the ending rounds. However, FTA is a profile fault attack method, which means that there is a profiling phase in which we perform a template building. That means the template is built based on fault propagation from the device. And there is a matching phase in which the internal states in the target device are retrieved by matching the fault propagation patterns with that in the template. FTA can also operate in the middle rounds because it doesn't require access to the plain text or ciphertext. But the question that we try to address in today's presentation is whether we can make FTA more systematic and identify practical fault models to be effective for threshold implementations, which are often very nice countermeasures against against side channel attacks, and also has got the seems to be have like natural defense against fault attacks because of their inherent randomness in generating the shares on which the computations are being performed. So whether we would like to investigate whether FTA can be extended to attack such protections without requiring ciphertext access. So the fault model that we use in our attack is what is called as a double error upset or double event upset, which is a specific example of what are called as multiple event upset. So in multiple event upset, a multiple transient fault occurs in a sequential cell. The double event upset has got multiplicity of 2 and can be characterized by 2 important variables. One, which is T injection, which is the fault injection time when the value of a target register, say R, has been corrupted, and T release when the fault is being released and therefore the register restores back to its original configuration. So we would like to kind of denote a fault model or a fault instance by this model, which is dependent upon, like R, which is the target register, T injection, that means the injection time, and T release. And the difference between T release and T injection is what is called as the duration of the fault. So the TI that we target is defined in what is called as a probing security model, which means that the attacker can access or observe the values of up to D intermediate wires of the circuit per bit during the computation at a given time instant. I would like to kind of emphasize that DEU is a first order because because even now we are targeting a specific register R, and that's a specific point on the circuit that we are targeting. And modern day lasers or electromagnetic setups can be potentially utilized for such fault campaigns. However, the focus of this talk is on how to build the fault templates for Boolean circuits and utilize them for attacking cryptographic circuits and implementations. So the technique that we use in our attack is called, what is called as a positive Davio's decomposition, very popular in the domain of formal verification. So let us consider a function f, or a Boolean function f, which operates on n Boolean inputs, say x0 to xn minus 1. The positive Davio's decomposition on the variable xi is basically decomposing function f into two parts. One, which is called as fxi bar, which means the part which doesn't depend upon the variable xi, and on the other hand, the part which depends upon the variable xi can be written as a conjunction of xi along with del f of del xi. Now del f of del xi can be again split up into two parts, which is a Boolean XOR of the function f computed on x0 to xn minus 1, but xi being set to 0. Along with we do an XOR with f of, again, f being computed from x0 to xn minus 1, but now xi has been set to the value of 1. I would like to emphasize that throughout my talk, the plus notation denotes modulo 2 addition. So if you consider a stuck at 1 fault at xi, then it is trivial to check that the fault will propagate to the output if and only if xi is equal to 0 and del f of del xi is equal to 1. So let us try to apply this on a concrete case situation where we are targeting, say, the present S box, the present, which is a standard lightweight block cipher. The S box is a 4x4 Boolean function, a combinational, and it can be represented as a combinatorial logic. So let us consider where the fault is, say, targeting the variable x1. So therefore, in order to investigate the condition, we apply the positive Davio's decomposition, del f del x1, and equate that to 1. So in that case, we obtain the possible values of x0 to x3, and we obtain that there are 4 such possible candidates which satisfies this equation, this condition. And likewise, when you consider a stuck at 1 fault at x0, then the condition can be written as x0 equal to 0 and del f of del x0 being equal to 1. So in that case, we again obtain a bunch of values for x0 to x3. And now if the fault propagates in both the cases, then if you can apply intersection, then you get only one single possible value which survives both the tests. I would also like to mention that if the fault at xi doesn't propagate at the output, then you will have a disjunction, because that would be the complement of the condition. So then we have the condition in that case would be xi equal to 1 or del f of del xi equal to 0. So in that case, again, the number of variables will reduce by 1, and therefore in the worst case, you will be requiring still maximum 4 fault injections. So therefore, in the best case, we probably require around 2 fault injections, but in the worst case, we will be requiring 4 fault injection. So at this point, we can also differentiate this attack from what is called as safe error attacks, which always requires 4 fault injections to get the 4 bits. But in the case of FTA, the number of faults can get down to 2, and therefore it shows that the technique is fundamentally different from a safe error attack. So now that means that now we can define the fault template, which can be characterized by a vector Sn for an n variable Boolean function. So Sn is a 0, 1 vector. In particular, the ith bit Si, if it is 1, then that means the fault propagates, and the condition is the conjunction of xi equal to 0 and del f del xi equal to 1. Whereas if Si equal to 0 means that the fault doesn't propagate, and therefore the condition is xi equal to 1 or del f del xi is equal to 0. So now here is the description of the target that we attack, which is the threshold implementation. The threshold implementation essentially is a technique of protecting against sites and attacks using techniques of multi-party computations and secret sharing. So in this case, suppose you have got an n-bit Boolean function which operates on n input bits, then each of these input variables is being decomposed into, say, Sx shares, and the computation is being done using vectorial functions, so that the output also has been kind of split into S shares. And the idea is that if you combine these S output shares, then you should get back the original output of the Boolean function, because you need to ensure that your function is correct. So here is an example of a TI being done on the present S box. In particular, the S box can be decomposed into 2 Boolean functions, f and g. So we only target, say, the f part of the Boolean of the S box. So the way to read this Boolean, this representation is as follows. So you can see that each of the component functions like f10, f20, f30 are the 3 output shares for the first output bit of the S box. And likewise, f11, f21, f31 are the 3 shares for the second output. And likewise, you can obtain f12, f22, f32 for the third output bit, and f13, f23, and f33 for the fourth output bit. We considered a multi-cycle implementation of TI, which means now that there are 12 clock cycles from T0 to T11, each of them computing these Boolean output shares. We consider a double error upset fault location at the locations x03 and x21, which are the the registers storing the masks, and we show a systematic method of how we can obtain the unshared bits x0, x1, x2, and x3, which the TI tries to hide. So here is an illustration of the attack. So let us consider the fault being done at the x03 location, and we consider the fault duration from T0 to T4. We obtain the positive Davio's decomposition, and we find out that the condition is as follows. That means the fault always propagates if and only if x2 is equal to 1, or the shared or the other part is depending on the share. So that means that if the input is fixed, then x2 is equal to 1 with a probability 1 or 0, but the other shares are true with a probability of 0.5. That means if x2 is equal to 1, the fault always propagates, else it sometimes does not. This leaks the value of x2. So likewise, one can estimate x3 by considering the fault being done at x03, but now the duration is being shifted from T1 to T5, and you can now obtain the conditions showing as x3 is equal to 1, or again, the remaining part depends upon the shares, and therefore they occur with a probability which is around around 0.5. Hence, if x3 is equal to 1, the fault always propagates, and therefore this now leaks the value of x3. We would like to obtain the value or estimate x1, and in that case, for that purpose, we target again the fault on the same register x03, but now shift the duration from T2 to T6. The condition that we derive here is again looks similar, x1 equal to 1. Again, the remaining part are depending upon the shares. But here is an interesting case, and you can note that when x3 is equal to 1, then the condition x33 plus x31, that is, or x32 equal to 1, is trivially true, because the XOR of all these masks should give me x3. And this camouflages the leakage of x1, because that means that whenever x31, the fault always propagates, and therefore it doesn't allow the value of x1 to get leaked. So we would like to address this subsequently, but before that, let us see how we can estimate the remaining bit, which is x0. And it turns out to be very easy. We target the register now x21 and consider the duration from T4 to T8. And we found out a simple situation where the fault always propagates if and only if x0 equal to 1. So in this case, it clearly leaks the value of x0. So now we build the template for the TIS box. So here are the different unmasked states, x3, x2, x1, and x0. Each of them, for each of them, I've got the template denoted as tx, which is denoted by the variables p0, p1, p2, and p3, where any of these variables, say pi, stores the expected number of times the fault occurs according to the fault model fi, and whether it creates a fault or it doesn't create a fault. According to that, we consider the number of times that you get such occurrences of fault. That is the expectation of the number of times the fault is created in the output. And therefore, right, if your number of fault campaigns is n, then pi will be something from 0, where that means the fault never occurs, to n, which means the fault always occurs. And now we see that you can partition the inputs into different different compartments. But I would like to take your notice into this pathological case where you have got say the inputs 8 and 10, which are for which the templates are same. Why are the templates same? Is based on what the discussion that we had. You can see that among or between these two inputs, what only varies is x1, that is x1 is 0 in 8, but x1 is 1 in 10, and we cannot distinguish because x3 is equal to 1. So therefore, x3 being equal to 1, it hides the leakage of x1. So in order to address this, we considered another fault at x02, consider the duration from T2 to T10, and we observe that the positive Davio's decomposition now very interestingly tells me that the condition is, of course, if x1 equal to 1, we will get it, propagation. But the condition which depends upon the shares for x3 is the complement of what we had obtained before. If you notice that the positive Davio's decomposition here is 1 plus x32 plus x33, but in the previous case we didn't have this complement, and therefore in this case the propagation is the conflict only happens when the value of x3 is 0, and therefore, right, we are able to distinguish between these two inputs, because in this case x3 is equal to 1, and therefore this camouflaging doesn't create any hindrance at this point. And therefore, now if you extend this template from p0 to p3 to p4 also, to input p4, you see that the occurrence, or to observe, I mean, when you observe p4, we are able to distinguish between these two situations or these two inputs. It may be noted here that the incorporation of this fault now makes all the templates distinct, and therefore you have got templates where for every possible unshared inputs there is a unique template that you can utilize in your attack. So therefore, we now can go ahead to the template matching phase. Here is an experimental setup that we have using electromagnetic inductions. And interestingly, we found out that if the same configuration bit file is used for template building and is dumped on a different target board, which is a Sakura G2 board in our case, then the faults can be reproduced exactly with the already found parameters and probe superpositions. More details of this can be found out in our Eurocrypt paper. So using this, we can build our template matching, or we can go into our template matching phase. So the fault model can be stored by the vector that, I mean, when we are performing, n fault injections in the template matching phase, we obtain a vector W, which stands for the number of times the fault is affecting the output. And then we perform a correlation. And in our case, we calculate the correlation by calculating the squared distance, and we try to minimize the squared distance. And we assume that the correct input state will be minimizing this square distance. So some of the salient points that I would like to mention here are that the leakage of the unshared internal state of 2 successive rounds of a block cipher can be used to obtain the round key. However, in our paper, we kind of show how the internal states can be recovered. The proposed attack works only with the probability distribution of the occurrence of faults and does not need access to the plain text or the ciphertext. This makes the attacks works even for middle rounds. Although the ACA or the safe area attacks also are able to work on the middle rounds, but they can be prevented by a masked TI implementation, against which our technique of FTA star is able to still work. So we also provided a graphical analysis of for FTA star. I will be, for the sake of time, be quick here. So in particular, in these diagrams, we try to show that if suppose the fault is at the location x03, then from the diagram it is evident that all the input shares of x2 being involved in this computation, then it implies that they get leaked. Whereas if you observe the other dependencies of x03, you can see that all of them are on partial shares, and therefore, right, they do not really camouflage the leakage of x2. And therefore, while the leakage is like, similarly, we can also observe that if the fault is at x03, but it at a different location time instance t1 to t5, then it also leaks all the shares of x3, and therefore x3 gets leaked. However, there are some, as we have seen, some bad cases and good cases, which also can be interpreted from this diagram. For example, you can see when the fault is x2, it's clear that x0 gets leaked because there is no other conflict from other shares, other input shares. The bad case can be seen in the case of x03, where you can see while it has got the potential to leak x1, but x03 also affects all the possible shares of x3, and therefore it conflicts with the leakage of x1. In order to handle that, we can bring in the complementary fault size. For example, if the fault is at x02, and for the duration from t2 to t10, we see that all the shares of x1 gets leaked. But if you consider the leakage of x3 too, that unlike the previous case here, as you can see in the green shades, we have shown you instances for the x32. Yes, I mean, while for x3, while it also, like in the previous case, while it also affects all the possible shares of x3 and therefore should conflict with the leakage of x1, but the condition is complementary as shown in this positive Davio's decomposition, and therefore while in the previous case the leakage was being was getting hindered when x3 was equal to 1, in this case the leakage gets hindered when x3 equal to 0. So the faults at x03 from t2 to t6 in the previous case, and the fault in this slide showing at x02 from t2 to t10 are complementary. So we also perform experimental results in order to evaluate the sanity of the attack. So here is a plot of the least square distance with different possible internal states, and we find out that for all the possible internal states, irrespective of the internal states, the leakage happens. For example, in this particular slide, we can see that when the internal state is 0, then the least square distance from 0 gets diminished to 250, at around the fault position of 256, and becomes minimum compared to the other possible candidates. So likewise, you can see for different possible internal states, the leakage happens, which means that the technique is irrespective of the choice of the internal state. So to conclude, we show that a new class of fault template attack, which we called as FTA star, which relies upon a fault model which is called as a double event upset, or DEU, and it can lead to effective fault attacks by creating templates during a profiling phase. Finally, the key is obtained during the profiling phase. And the graphical analysis is being developed to further systematize the analysis and show that TI is inherently not faultless to false. So with this, I would like to say thank you for your attention, and I would be happy to receive any queries. Thank you.